Okay, now we have understand what is the core computational step of the attention uh, component, but to form that is practically useful computational blocks that we can use to construct the data models, complex data models to deal with real data. There are some practical tricks to apply. Before we introduce those tricks, it would be helpful to get ourselves well motivated by looking at how the attention blocks work in a data processing pipeline. The attention blocks are often used to form a series of data transformation, which we can consider to encode the representation of the data, so to reveal the relevant information to the tasks. So here we have some input data, and as discussed, which consists of multiple units. And we apply the self-attention, that's a unit to compute how to form a new kind of representation of the data by consider how the different parts of the data related to each other in this attention block, which will give us a new representation of the data. And this intermediate format will be sent to another block of attention and get the new representation, so on and so forth. So that makes the data processing pipeline. Conventionally, if you read papers in the literature, you will often find those models are represented in this way, such as you have the input data, and which is given to attention block, and this attention block then feeds its output to the next attention block. So we stack those attention blocks together. Because in each of the processing step, the data, the model is given a chance to let the data to look up within itself and to find its the relationship. So it is a great way to find interconnections in different locations or different units of the data, and use those discovered relationship for the task. And the first very often used technique in this procedure is, instead of just sending the transformed data in this pipeline in each of the model, which is often also used in other kind of computational steps. This technique is agnostic of the fact that this is the attention model. Okay, so we kind of shortcut here. We let this model to take its output and combines. By combining, I mean element-wise add up with the original data and give this to the next step. So this procedure is repeated. So instead of having this, this kind of technique is called residual network, which you might have been encountering in other modules, even in this very subject. So in attention models, we use this as well, which facilitate the supervision information to make it easier get the training signal to reach the lower down blocks, like here, Otherwise, if you want to calculate how about if I change this motor parameter, what will be the effect on the final output, you need to go through all these models, which can get the supervision or the training signal difficult to participate all those complexities. So for one thing, and for the next trick, that is, we can control the self-attention, the range of the self-attention where it is computed. For now, the attention is computed among all possible pairs among the parts in one data sample. This is sometimes desired. For example, if you want to understand the meaning of the data, and after all this transformation, you want to get some representation of the entirety of the data. This will encode all the relevant information, and you want to form some classification or other kind of decision making. This is okay, but for some other applications, it might be useful to limit the range of attention the data can pay. For example, in natural language processing applications, we can use this select attention mechanism as decoders. By decoders, we mean we will let the model to generate the prediction of what the data should be, or could be, or is probably or plausible next observation from the existing ones. So for such a typical application, you would have something as start, for example, A, maybe, and the entire data is empty, except the first one is an A, which is encoded. We'll encode that into some number, which we will introduce this technique later. And you want the model to predict what will be the next word. Let me move this representation here to make it easier. Okay. So to predict this word, it will not be very helpful if you let, for example, let's simplify the intermediate steps and only consider the input and the output. It won't be very helpful if you let the output to attend somewhere beyond what you have now. So for the next steps generation, well, let me call this A, and the next step will be here. It can only refer to the previously generated parts. Okay. This is called autoregressive decoding. For example, for some reason, the output of the model find there are some high probable words which may include some nouns. See if it happened to sample from the probability word dog, which is of course sampled from the dictionary, and the prediction will be the probabilities among all the vocabulary in the dictionary. And in the next step, to predict this part, the model needs to look at these two parts. So for example, maybe 8 would be a proper word if you apply to a dog, and you would see maybe wrote will be less probable, and that is how those kind of models works. Okay, and maybe the next one A, okay, and the next one a hot dog. So when it comes to hot dog, you can pay attention to the previous generated words in the sentence. To implement this mechanism, we would like our attention model to be able to focus the relationship in a range. For example, remember when we have the attention matrix, okay, and we want to use this matrix to compute the output, we will be combining the values at each position. Okay, I think I have hide my window. We will combining the values at each position using the corresponding attention weights. So to compute the first output, we are combining all the values at all locations, which is exactly what we don't want kind of behavior in this application. What we can do is we can forcefully to zero out all the attention weights that is beyond what is allowed in this range. So we can only compute its attention at this location with the first location, which is self. When we compute the output at this location, it will be allowed to pay attention to the first two weights. And we need to zero out. Let me use a blue pen to represent those entries that have been zeroed out. And so on and so forth. When we consider the maybe ith output, we are allowed to pay attention to the first I entries, first I units in the data. So basically, we can put a mask on the attention matrix, and the mask will take the lower triangle of the matrix. So this is another very useful kind of tricks. Beyond these, we also adopt some of the usually adopted techniques to stabilize training or to regularize the model training, to ways to make the model more generalizable and more trainable. We will introduce those techniques when we encounter them. Okay. But the main structures we need to build into the attention model is the residual link between the attention blocks and the optional masking of the attention weights to show there is a temporal, there is an order in the unit of the data. For this reason, this mechanism is sometimes called causal attention.